Okay, in the next example, I'd like to remind you that on your trig identity paper, I showed you the most popular version of the identities, and I said you are supposed to be familiar with the other versions of the identities that you get by manipulating the first version. So reminder, if you subtract sine squared u from both sides, you are going to then get this version of the first Pythagorean identity. So you're supposed to be familiar with the most popular version of the identity that I showed you in the highlighted yellow, and you need to become familiar with the other not as popular versions of the identities that I highlighted in pink. When I tell you, hey, I've seen that before, I think that's equal to something, it's because you're supposed to be aware of the most popular version of the identity highlighted in yellow, and you also must be familiar with the not as popular identities in pink. Is that making sense? Now, I'm reminding you of that because that's going to be important in the next problem. I believe that's a popular one. Right there. Do you understand that 1 plus tangent squared x, or 1 plus tangent squared u, is the same thing as tangent squared x plus 1? Are you familiar just switching the order of the 1 and the tangent squared? It's the same thing. So the yellow highlight becomes secant. The yellow highlight becomes secant squared, and I'm going to change the u to x. We're using x. So since we're using the variable x, I'm going to change the u in the identity to x, because we're working with x. So yellow highlight becomes secant squared x. All right. Well, what's the orange highlight become? That's cosine squared x minus 1. All right. I'm not seeing that anywhere. That's not... Ooh, yeah, it is. Hold on. I need to do this. If I subtract 1 here and I subtract 1 here, I could get a new version of this. Cosine squared u minus 1, cancel, equals negative sine squared u. All right, so not only do you need to be familiar with the yellow, not only do you need to be familiar with the pink, you need to realize that all of those pinks could be modified, and you could maybe get similar expressions in blue for each of these that I'm not showing you all of them. Does everybody see how blue highlight is just a little bit different version of the pink highlight? And there would be a different version of all the pinks. So when I say you need to be familiar, that looks familiar. It's because it might be a yellow Pythagorean identity. It might be an equivalent form in pink. It might be an equivalent form in blue. So the orange expression is going to become negative sine squared x. Green becomes green. I've seen green before. Green becomes green. And blue becomes blue. And I'm done. I've verified. Oh, by the way, at the start of the problem, because in my brain, at the start of the problem, in my brain, the left side was the more complicated side. So I started working on the more complicated side, and I knew I was going to be done when I got negative tangent squared x equals negative tangent squared x. Any questions on example 3? Okay, I'm going to do example 4 on this one as well. This was kind of a quick and short one. So in the next one, I'm going to, in my opinion, I think that adding and having two terms, is more complicated than having one term. So I'm going to start on the left side. I'm going to start on the left side because, you know what, I think I'm going to try the concept of convert everything to sines and cosines. I think I'm going to use convert everything to sines and cosines. So for example, tangent of x is sine x over cosine x, and cotangent x is cosine x over sine x. And so I know that I'll be done when I can get secant x times cosecant x equals secant x times cosecant x. So I'm going to work on the left side. Now, I'm adding fractions, so you have to be comfortable with adding fractions. So, to the left equation, I'm going to multiply by sine x over sine x. And in the right equation, I currently have cosine over sine. I'm going to multiply by cosine x over cosine x. And now I have a common denominator. Both fractions have a common denominator of sine x cosine x. I got a common denominator so that I can add fractions. My left fraction has a numerator of sine squared x. My right fraction has a numerator of cosine squared x. And I'm simply going to rewrite this as sine squared x plus cosine squared x all over my common denominator of sine x cosine x. All right. Famous saying. I've seen that before. Yellow becomes yellow. That's the famous Pythagorean identity. Sine squared x plus cosine squared x equals 1. You might look at this and say, Mr. Lehman, how are we going to finish this out? I'm not sure how to get that. Well, the key is understanding how to multiply fractions and how to break them apart. 1 over sine x times cosine x is the same thing as 1 over sine x times 1 over cosine x. So you've got to be able to take this single fraction that has two factors in the denominator. In the denominator, you have the factors sine x and cosine x. And to break it apart as two separate fractions multiplied together. And now finishing the problem should be easy. You've seen pink before, and you've seen orange before. Orange is secant x, and pink is cosecant x. They're backwards. So again, you're allowed to, the commutative property of multiplication, you can switch things around. 2 times 3 is the same thing as 3 times 2. So cosecant x times secant x is the same thing as secant x times cosecant x. So you can just flip them around. Check. Done. I'm done example 4. I've verified example 4. And I'm going to end this video now.